Uh, Give me a few seconds, let the recording begin. Okay, so what we will be looking into in today's lecture is heap data structure. I think we are implementing more and more a slightly complex algorithms more and more, and from next lecture onwards, we will be looking more into dynamic programming. So very and some of the tree based algorithms, some recursion trees, lot of we will be seeing a complex data structures. So when we study the complex data structure, it's very important that we always study a data structures with respect to its uses. So as I say that the real skill in data structure is not knowing what are linked list, but to know where to use linked list and where not to use linked list. Likewise, we have a lot of data structure. A true skill in data structure is when you master the knowledge or when you master a skill set where you know that where I need to use a specific data structure and where I shouldn't use that. So I think from our earlier lectures, what I could observe is most of you had no knowledge of heap data structure. So in today's lecture, we will devote the heap only to understand that heap data structure and how to implement it in Python. So in case in Python, if I want this data structure, what should be a way to realize this data structure, store elements in Python? Fine. So now, what we need and what we want is to see what is heap data structure. Let me tell you what exactly is a heap data structure. So heap data structure is it's nothing but it's a tree-like data structure. So it's a tree-like data structure, and we have two types of heaps. The one is we call it as min heap, and the other he is called as max heap. Okay, so what is this min heap in max heap? Let us look into this. So let us suppose I have this few elements like 1, 5, 9, 2, let's say 0. Oh, so if I have this set of elements, and right now here n is equal to 5, so I mean I have 5 elements. So you can think of this as a array or a list of numbers or set of numbers. So these numbers can be stored either as a set in Python or as a list of numbers or as a tuple. We can store it in different ways. But what does it exactly mean that when I store them in format of heap? So let us specifically see what is min heap. So we will now be storing these 5 elements in the form of min heap. So when I say heap, the elements are stored in form of a binary tree. What? So basically, how are the elements stored? Elements are stored as a binary tree data structure, but this has few conditions. So these conditions make a binary tree as a heap. For example, so what is the first element we want to store it in this is 1. Let us take 1. So when I want to store 1 in the tree, I create a node with value 1. Then I take element 5. So what I do is I add the 5 as a left child of this, right? And when I add a new element to as a left child to this existing node, what I see is I see the condition. What is the condition? Always the child element's value should be less than the parent, or you can call it as root. Fine. So is the okay? I think okay. So if we are talking about min heap, this would be greater, right? So this is min heap. When child value is less than parent, the tree becomes max heap. So in our case, if I want to stick to this definition of a min heap, it means that the data in the parent node or a root node should be always less than the data in the child node. So for a min heap, what conditions we have satisfies? Child value less than parent node or child value greater than parent node. So min heap means the parent nodes or a root nodes value will be always less. If I say max heap, what does it indicate? That the parent's value will be always greater than the child value. So this is max heap and this is the definition of min heap. So right now we want a min heap. So we will be checking the condition for min heap. So for a min heap, let me just do a control and let us. Okay, so for a min heap, what should be the condition? The condition should be child node's value should be greater than the value in the parent node or root node. So after inserting 5 as a child of parent node, is this condition satisfied? Yes, the child value is greater than the root node, fine. So after that, you have another node to add, and I have a space as a right child of this. So I add this as 9. Then after adding 9, I have to add 2. So we always start with the level wise. So the tree grows as a level wise. So 2 will be added as a left child of 5. But after adding 2 as a left child of 5, you can observe that. So every time when I add any node to this binary tree, I need to see if this condition is satisfied for this tree or not. So this condition should be satisfied at the each node level, at each level. I mean, at each parent node level, this condition should be satisfied. But after adding 2, what you have observed is this condition is not getting satisfied. The child value nodes are greater than parent node, whereas as per this condition of a min heap, what I want the child value nodes to be less greater than the parent nodes, parent or root nodes value. So what I do, the solution which I have to swap them. So what I do is uh, this here, this will be 5 and I'll take 2 here, right? So for this the condition is satisfied, for here the condition is satisfied, right? So this would now look like sum of this, like 1, 2, then 5, and here I have 9. So look at all parent node 1. Is this value less than both the child value? Yes. Here, this is another parent node here. So is this value less than child node? Yes. So we have added 2. After adding 2, the last remaining element is 0. So where do I add 0? So I need to fill level wise. So that's how the tree grows in this way. Always tree goes level wise. So this node will be added as a right child of this. Now, after adding a right child, is this condition satisfied? No. So what we do is we do a swap operation for this. So when we do swap operation, I mean the child value will be stored as a parent node will be stored as this. So what happens is it becomes 2 and here it becomes 0. And when you add 0 here, you can see that even this condition is being violated. So another swap occurs at this stage. So 0 goes here, 1 comes here. So in the end, this tree would look like 0 as a root node, then 1, then I have 9, then one has a 2, this one with 5 and another with 2. So this representation for these elements will now be called as heap. What I call it as heap. And specifically, what does this property, this satisfies this property? So we call them as min heap. Why? The parent node value will be always less than the value inside child node. So this is called as min heap. Now, what is an advantage of this? So if I, okay, I think you have this tree, right? Let me go to another frame. What was that value? 0. Then I had a 1. Then I had a 9. 2, and 5. This was the heap, right? Now, this is a heap. So, once you form a heap, the advantage or what are the properties of a heap? The properties of a heap is that the root node of this heap, the root node of this min heap will be the smallest element among all the elements present in this. Are you getting this property? So what is the property of a heap data structures? If I talk about min heap, root node will be always the minimum element in the heap. Are you getting this? And as in case of max heap, the root node will always be the max element in this in the set of elements stored in the heap data structure. So heap is also used to sort elements. So how do you use the heap data structure to sort elements? For example, we had this array. What was that? I think what was that array? I think one. It is 15920. 15920. These were elements. So we have stored them in a heap format. After storing them in a heap format, if I keep on removing, if I keep on deleting this root node, for example, once I have formed a heap node, I know that the root element of this heap always is the minimum element. So I can use this property to sort this array. So I will take these elements, construct the heap. After constructing the heap, you can just keep on retrieving element from a root node. So if I want to do a sorting on this, if I want a sort operation to be done, what I'll do is I'll just remove the root node. If I remove the root node, what's the element I get? 0, the minimum one. Now situation becomes slightly complex. Now I'm saying that this root node is being deleted. So I have two options. If any element in this is deleted, so someone should be replaced, right? If you want to say that you're going to remove this node, something should happen, right? So what happens here is, in a heap, whenever you never delete a root node, what you do is, when I say I'm removing element from a heap, this value is replaced. So what exactly happens here is, whenever you want to remove this element, this 0 in this is removed. Remember, root node is not deleted, the value inside this is removed, and in place of this, the last node, this value gets occupied here. So 5 will come here, and whatever 5 which went here, now this node becomes empty. And does this node have any child associated with this? No, both are null. So what we do is, we delete this node. So deletion in a heap occurs in this way. How does it occur? Whenever you want to delete a root node is not deleted, the value within that root node is removed and it is given to the user. Then the whatever the last node of this heap, I mean, you need to go level wise. So level 1, level 2, and level 3. So whatever the last node which you see here, this value is replaced for the root node, and the last node which does not have any child nodes associated with this is entire node is deleted. So memory is freed from the last node, not the root node. Okay, so after deleting that, what is now the new heap? 1, 5, 1, 9, and 2. But remember, the moment you placed 5, you are violating the condition. What my condition expects that, my condition for min heap expects that the root element should be always less than the child element. So I have a 5, you have compared with the left child, it looks like it is violating. So what we do, you swap it. So 1 comes here, and 5 goes here. So after swapping that, you will check the condition. 1 less than 5, yes. 1 less than 9, yes. So you are moving to the next level. Under the next level, what are you seeing here? Is 5 less than 2? No, condition is violated. So 5 comes here, and 2 goes here. So instead of 5, it becomes 2. So after deleting this 0 element, what is the modified heap? Let me write it. So element here is 1, this 1. then 2, 9, and 5. Right. So once you remove element from a root node, this reheapify always works. So heap is automatically maintained. So if you implement heap data structure, you need to write this code to reorganize the elements in this heap upon deletion of a root node, so that the entire tree once again comes into a min heap format. So after now, once you reheapify, you what you do is you take this one again. So the next minimum will be 1, right? After taking next minimum, you once again reheapify that. So probably what happens is 5 goes here, it gets changed. After that, it will once again reheapify. The reheapify works on. So heap converting these elements into a proper organized way, so that this condition for min heap satisfied, it occurs after each deletion. So you keep on deleting the root node, root node, root node, and you get elements in minimum one, 2, 9. And this way of sorting these elements with the help of heap data structure is called as heap sort. Okay. So I hope you understood this. Just quickly raise your hand if you have understood this. Okay. Okay. So yes. Now that we have seen what is heap sort, let us do one thing. See, what course we are studying? We are studying design and analysis of algorithms. So studying this doesn't make any sense for that. We are just known the concept. But as you all know that for any data structure, any algorithm which we said, we have to always worry about the time complexity of that. So let us look about the time complexity. So now when I want to look for time complexity, let me just go back and get this one. Okay. So how does heap sort work? So these elements have to be converted into heap format, and from heap, I now will be getting a sorted array. So 0, 1, 2, 5, 9, right? So from this to this, I get a sorted array. So if I want a complexity of this, there are two processes in that. What are two processes? First process is to convert this array into a heap, then keep on removing element from this heap, so that I keep on getting first minimum, second minimum, third minimum, fourth minimum, and the last minimum from this array. And the moment I keep on getting the minimum elements, I got a sorted order. So sorting is achieved. So what would be the complexity? So first let us look the complexity of this process, the process here. Now what is the size of this? It is size of this is n, size is n. Now, so I have n elements. From the n elements, I am now constructing what I am constructing. I am constructing a binary tree. So, do you know what is the complexity of inserting a node in a binary tree? So every time I am reading one node from it, and I'm inserting in a binary tree. And of this, and from this, if you specifically look into this, what I am doing is I am trying to store this in almost in a format of binary tree, wherein I have some kind of order. What is this order? The order is that the parent node's value should be less than the child node. So if you recall the way these ordered binary trees occur, so you can even visualize this, or you can even correlate with the definition of binary search trees. So whenever we go for some kind of ordered binary trees, we know that in order to insert a node in a binary search tree, the insertion complexity of storing any element in binary search tree is log n. So one insertion operation cost the cost of log n. Okay, I think this you might have studied it in a data structure. So I'll not go dig deep into this and tell you why it is log n. So this was covered while learning data structures, where you will find that for any order, I will always go for less, left, right, and all that. So you can also see that. I hope you understand that. You can also see that the order is maintained by traversing the levels. So you add a node here. For example, you are adding a node, but this is compared with a few values. This goes here, this goes here, and it gets replaced there. So it is all a level wise traversal. So this value here, whatever the value which you insert here, this never gets compared with all the values in a heap. So it compares with almost half of the tree values, like your binary search tree or your binary search algorithm. So inserting an element in this heap would take log n complexity. So n indicates the total one. So I have n elements. I have n elements, and out of n elements, if I want to construct a heap, I do log n times. So n times log n operations I do, that forms the heap. So the complexity of this process will be, I can write it O of n log n, right? And once I form a heap, now every time I need to just keep on removing the minimum element. So how many elements you need to draw? N elements you need to delete from this tree. So how many elements? Deletions are n deletions. And you should know that after deleting one element from this heap, once again the heap is checked for the conditions validity. And going on the same logic which we have looked at while inserting the node, a similar logic also works while reorganizing these elements in the heap, so that they can be in a proper format which validates the conditions of a min heap. So going on this, even deletions would also take log n operations, exactly same as binary search tree deletion operations. Instead of saying similar, so deletions also take log n operations. So n minimum elements you have to retrieve, and every time you're taking that, it takes log n operations. So the complexity of this entire operation of deleting and forming is n times log n. So what is overall complexity? O of n log n plus O of n log n. What would you get? You would get a 2 n log n. So when you take a big O of 2 n log n, this 2 is constant, it moves out. So the overall complexity of a heap sort, what it would be? It would be O of n log n. Okay. So are you getting this? The time complexity. The time complexity of a heap sort, I mean, a heap based sorting algorithm will have a time complexity of O of n log n. And what is the complexity of constructing a heap? O of n log n. Okay. And can you tell me what is the complexity of retrieving a minimum element from the heap? So just okay. Raise your hand if you have understood why the complexity of heap sort is O of n log n. If you have understood this. Okay. I think I have a question. Omkar has a question. What he is asking is, sir, why we need to reheapify if we can pre-order traverse the tree for sorted array? Remember, if you talk about heap, the example here which I have taken, it gives you a sense that if I do a pre-order traversal, I might get a sorted one. But remember, the only condition here I am putting is that the parent node's value should be less than the child node. So the way we started inserting them, you felt that left side value will be, you cannot guarantee that the left side value should be always less than right. These conditions I am not talking about. If I put this additional condition, then you can say that you are pre-order one. But remember, here we do not put this condition. It is not mandate. If you want to put, you can put it. But the problem is that when you put this less than condition, deleting a node might be a little bit complex. So deleting a node would now become as complex as deleting a node in binary search tree. So instead of just checking this and that, I need to even check whether left is right, right is left, or all that. So that's why sometimes we relieve this condition and we do not enforce any specific order on this left value and right value. Since we do not enforce this condition, we cannot go for that pre-order traversal. So if we do not enforce, and if we have enough proper use case, we can see that pre-order might not give you exact value you intend to get that. Okay, fine. So I hope you understood this. Why the heap sort is and log and that. So now, if I ask you a question, if I have a heap, okay, let me get what was that heap? 0, 1, 9, uh, 2, 5. This is a heap. Given this is heap, can you tell me what is the complexity of getting minimum element from a heap? What is the complexity of getting a minimum heap value of getting minimum element from a heap? Can you type that in chat window? Think and get the answer. So what I'm asking is, what is the time complexity of getting a minimum element from a heap? Yes, it's a O of 1. It's a O of 1. I think let me also touch the answer given by Onkar. Onkar says, can it be log n? What he has asked is, can it be a log n? So what we do is the yeah. So it could look like a confusing thing, but when you see here, this operation of retrieving the minimum element is at the top of root node, right? Remember what I am saying is, I am when I say I want minimum element, I am not deleting it. Remember, I just want from this all elements, I want minimum element. So what you will do is, you are not deleting this, you are giving this value out. See, the minimum element of this entire heap is 0. So when you are retrieving this, you are only retrieving the value, you are not deleting that. I hope you understood. You are not deleting that, you are just retrieving that. So retrieval itself is O of 1. If I ask you deleting the minimum element from the heap, then okay, then you can say what it would be. It would be log n. Are you getting? I hope I understood your answered your query. Yeah, it's actually a good thing that you got that value. And we should always understand that the core objective of heap like data structure was to facilitate what I say, it was to facilitate a data structure, design of a data structure which can give me the minimum element in O of one comparison. So once I put that into a data structure, the core objective of this to get it in O of one. So removing element. So if I ask you the removing the smallest element from the heap, it is log n. Inserting a new element to a heap, log n. Removing a minimum element from the heap is log n, right? So now let us compare the heap data structure with some kind of array like data structure. So if I have an array of n, let us say some elements 2, 3, 5, 7, 8. Let us call this as a list. Okay, now let us talk about list being some indexed array. So here I am saying array. You can say Python list or some kind of array in your C and C++. So this is your linear way. This is your heap. If I want to compare the complexities of CRUD operations, so if I want to compare the complexities CRUD operation for create means for inserting a new element in a heap. I think, let me say. So I'll take list and I'll take heap. And we will try to write the complexities of CRUD operations. Like create means adding a new element in a list, adding a new element to a heap. So adding a new element to a list, what will be the complexity? When I'm saying list, I am talking about indexed data structure. What I'm talking about? Indexed data structure. That too, what kind of it is? It is a linear data structure. And heap, what is heap? Heap is a non-linear data structure. I hope you know what are linear and non-linear data structure. So in linear, okay, so I'll not discuss this. I hope if you have that, you can ask a question. I'll explain you what is the difference between linear and non-linear. So list, I'm talking about linear index data structure. It means lists in Python and array in your C, C++, and Java. That's what I'm talking about. So in this, if you want to insert a new element, and I'm saying inserting a element. So if I say inserting a element, think of a random case. I'm not saying that insertion at the end or insertion at the beginning. I'm talking about a random case. Means it could be at middle of the array, it could be front and back. So I'm talking about a random position. So given a random position, so this element can be inserted at any random position. What would be complexity of inserting into a list? We know that for a heap, the insertion complexity would be O of log n. But for this one, but for create in list, can you type it in chat window? N, yes, you are right. So the purpose of this, when I say indexed, so I have array something like something, 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 and that. I want to insert something, you have to re-index, you have to move front and all that. It will take O of n. So reading any random element in this in index. So if I want to read any random element from the list, what is the complexity of that? Index data structure reading any random element is O of 1. But in a heap, you cannot read any random element. The overall purpose of a heap. Okay, random is there. So here in a heap, it is not designed to get any random element. So if you want to do any random element, what you need to do is you need to retrieve all the elements from a heap and compare which is your element. So here it could take n log n. So n times you are reading all n elements in a heap in log n types. During this, you are comparing if your element which you want to compare, for example, the key which you want to compare, you are comparing that. But in case of linear indexed arrays, whenever you want to compare any random one, you can directly go to index and you can see retrieving that element by index O of 1. But if you want to retrieve a minimum element in a R, and assuming that this is not sorted one, what you need to do, you need to first apply O of n log n of sorting. You have to sort them. Then even if array is sorted, if you want to get minimum element, the complexity would be O of n. Okay, because you need to remove element and you need to get that. See, remember here when I'm saying read, I am talking about getting the element along with that memory location. So in case of heap, if I want to retrieve a minimum element every time, the minimum retrieval is O of 1, and along with retrieval you want to delete that from the heap, the operation would be O of 1 plus log n to reheapify. So it would be log n. So retrieve, remove minimum element from the array. Minimum. So what I'm talking about is retrieve and delete. So this operation I'm talking about is retrieve, read and delete the minimum element. This operation I'm talking about, read and that. Only just read might here it is take one. It might take n. You want to retrieve the minimum element. So when I'm talking about retrieve and delete, here it would be n, here it would be log n. So this is where you get a benefit. This is far better than n way of doing it. Update will be O of n, delete would be O of n, and here in this case, update would be log n, and delete would be even log n. So this comparison chart should give you idea when I should use it and when I should not. Okay, so now tell me, I have some. Let us suppose now. Okay, let us come back to our example of Prim's algorithm, Prim's or Kruskal's. So in a Prim's or a Kruskal's, what I have is I have edges like 0 to 1, some cost 2, then edge from 2 to 3, some cost 4, and edge from 3 to 4 from cost 6. And if you recall our working of Kruskal's or a Prim's, we sort these edges based on this cost value. Okay, and every time while implementing those algorithms, I think even while implementing Prim's algorithms for Kruskal's and even the single source shortest path, I mean the Dijkstra's algorithm, you could have seen that every time I wanted a minimum element. So for example, minimum from these edges, minimum from the list of unvisited nodes, minimum from the set of elements which we have. And every time I do this, I remove this edge from this and I insert into another set, visited edge, unvisited edge, and all that. So after removing that, next time when I want to retrieve, I had to retrieve the next minimum, right? So theoretically, we saw that we do minimum and all that. But now tell me, what would be the best data structure to represent these values? So I need to store these values in a such a data structure where I'll be keep on removing the minimum elements from that array every time from that data structure. So based on this comparison, if you store them, for example, if you store them in a linear array, I'll tell you what's the problem when you store them in a linear array. So you have stored a numbers in a linear array 1, 2, 3, 4, 5. I want a minimum element. Yes, you have retrieved it in O of 1, but I want this element to be removed from this. If I want this element to be removed, the conversion of this linear array from 1 to 4, 5 to uh, 2, 4, 5. What is, see, retrieval is O of 1, retrieval is O of 1, but I want this element to be removed. Removal operation is O of n, because when you moved it, this has to be re-indexed. So n re-indexing O of n. But think of if this is being stored in a heap format, so in form of some heap. So retrieval of minimum element is O of 1, and if I want this element to be deleted from this, what is that operation? O of log n. Now tell me which is preferred, list A indexed data structure, linearly ordered index data structure, or heap? Can you type your answer? If you feel such kind of things have to be stored in a linear index data structure like lists in Python, type 1. If you feel no sir, it looks like after comparing this, you have to only compare between these two, O of n or log n. Based on comparison, tell me if you want to store it in a linear index data structure, then it is 1. And if you want to store it in a heap, type 2. Which is best for such kind of things, 1 or 2? Yes, the answer is 2 because log n is less than n. Log n is less than n. Retrieval of minimum element you're getting in 1, but here you have to do log n operations. Okay, so now that we have looked here, I think for implementation we will do it in next lecture. But I'll tell you, in Python we have a module called as heap q. So with the help of this module in a Python, I can implement heap data structure. So now I think if you have genuinely watched my video where I asked you to go through implementation of Dijkstra's algorithm in a video, did you go through that? So all the students who have gone through that my earlier video where I implemented Dijkstra's algorithm, one question: did I use this heap queue data structure in that? Yes or no? Did I use heap queue data structure in that? Yes, I have used it. So now you will get an idea why I have used that heap queue data structure. Okay. So since we are nearing the end of this lecture, and I think you might be having other lecture as well. So what we're gonna do is we will see. What I'll do is I'll share some links to you where you can um, try how to implement heapq in Python. Maybe you can try it in a practical session. But now it should be clear to you why I was using this heapq data structure in Dijkstra's. Maybe I might have even used it in a Prim's algorithm and Kruskal's implementation as well. So I think if you check the code which I've written in a GitHub repo, which you will find there, most probably I might have used this heapq data structure there as well. Okay, so fine. I think yeah, that's it for this lecture.